Thanks for hanging in, everybody. Hopefully that coffee will keep you awake for the next 45 minutes. You may know Northeastern University, where I work as a Boston-based private research university that's been around for over 100 years. And note that I work in Seattle. Over the last 6 or 7 years, Northeastern has created 7 regional campuses around the North America, 4 in the US, 2 in Canada, and now 1 in London as well. So I'm actually based in Seattle. I've been there over 4 years now, and I run a Masters in Computer Science program for about 400 graduate students, 50% of which are women, which is a good thing for us, I think. The campus is actually in a really interesting location. If you know Seattle, it's in an area called South Lake Union. It's just on the edge of downtown. And South Lake Union is also known as Amazonia, because basically we are surrounded literally by Amazon buildings. So whenever I stumble out of campus, it's almost impossible not to trip over an Amazon engineer or their dog, because they take their dogs to work. And what's really interesting is that because of Amazon's presence there, this has acted as a magnet for other tech companies. So any day now, Google Cloud Division is about to open about 3 blocks from our campus. Facebook have just opened a building 2 blocks from our campus, which is having another 2,000 engineers moving in. And Apple are moving in their AI people about 4 blocks away. So I live and work in a really exciting ecosystem. Much of the cloud developments that we probably all use are done very much in South Lake Union or just across the lake at Microsoft in Redmond. So not surprisingly, I see the cloud every day, and I kind of think nothing really exists if it's not in the cloud. So this talk is about clouds, and it's about how you achieve and analyze scalability in a cloud, given that there are costs to pay for scaling in a cloud. And analyzing these costs and scalability is difficult because they're distributed systems that you're using. It's a complex ecosystem of technology which you're using some virtualized resources within. And so what the talk will do is talk about a method we've been using to actually do performance testing and scalability testing of cloud services, and hopefully give you some insights into the way these systems behave. And it's not always intuitive. But first of all, let's pull some random numbers out of a hat. Talk about market research about cloud adoption. So if I'd have stuck these numbers up 7 years ago, they would have been very, very different. And I'm sure many of you 7 years ago would not have been using clouds, whereas many of you, I'm sure, already are. And one of the reasons for this is the ease of scaling your system in a cloud. You just can scale up to hit a peak in demand and then scale down very rapidly as the peak drops off. There's also the advanced services that you have in cloud technologies and cloud platforms, which are being continually produced by the cloud vendors. And you get this faster hardware, software refresh cycle. And as the quote says, using a cloud is a much better option than expensive, high-maintenance on-premise solutions. So increasingly, organizations are not acquiring and administering and maintaining their own systems, their own hardware, because compared to a cloud, it's a nightmare. And I'm sorry, whenever I see that evil clown, I think, let's not dwell on that one. So when I'm using a cloud, if I want to acquire some more hardware to throw at my system, I just go to my friendly cloud console and I deploy something, or I configure a load balancer, I configure some rules, I hit the go button, and within 5 minutes all those resources are available to me. Or if I'm using something like a serverless infrastructure, such as Google App Engine or AWS Lambda, this all happens for me as my demand grows and drops off. So scaling is a piece of cake, basically. Unfortunately, so these are 21st century skills. So this is what we teach our students. It's basically scalability at your fingertips. You can just go to a console, deploy new instances, deploy new compute resources. If you use the managed databases such as Dynamo or Google App Engine or the Azure equivalents, then you've essentially got an infinite storage capacity They manage it all for you. You don't really care where it is or how it's managed, what machines it's on. All of your data is managed for you. And if you use a pay-as-you-go service such as Lambda or Google App Engine, then you just pay as your spikes go up and down and resources get allocated. The downside, of course, is it costs you money. You don't have to have the upfront capital costs when you acquire technology, but as you're using these systems, you're spending money. You're being billed by your cloud provider. And this is not surprisingly, according to yet another survey, cloud optimization of costs is one of the primary problems that people are having in 2019. People are actually seeing, and I talk to people around Seattle all the time and hear this, that they're getting surprise bills on their cloud usage. Some of it is just like negligent use of forgetting that stuff's running. There's a couple of legendary stories about teams blowing $80,000 in a week because they forgot to stop down a test system. But some of it is just that it's really hard to predict cloud usage when you've got unpredictable loads hitting your system. It's easier to do reserved instances because they're cheaper, but when you run out of reserved instance capacity, then you have to get on-demand instances, and this costs you more money. So costs are a tricky issue in clouds. And you can see that some of the big end of town spend a fair bit of money on cloud systems. AWS makes an awful lot of money. And this is the reason. Capital One, they're spending $250 million on AWS. Last year, I think those numbers were. And so you can see that if we could think about ways to engineer our systems such that we could reduce our costs by even a small percentage, 10% maybe, then if you're spending $250 million on your cloud technologies, then that's a significant chunk of savings. So small optimizations at cloud scale can make real big differences to your costs. So let's just relax for a second, sit back and think about what's actually happening underneath from an engineering perspective. What we want is systems that we can scale, and when the demand grows, we can scale them very rapidly, potentially exponentially. And so this gives us the ability to grow our systems to meet increasing demand, and clouds provide all of those services. We also want to keep our costs low. We don't want our costs to grow at the same rate as our scale of our usage of resources, because that means our costs would start to grow exponentially. So we want to be able to grow our capacity, grow our throughput exponentially, but we want our costs to grow very slowly. I mean, ideally not grow at all, but that's kind of fantasy land. They're going to grow a little bit, but if we can engineer our systems so our costs grow very, very slowly compared to the amount of capacity that we're actually acquiring, then we've got what I call a hyperscalable system. We can continue to scale our capacity while keeping our costs under control. And if you want to read more about this, there's a chapter I wrote in a book that came out a year or so ago on the features and characteristics of hyperscale systems. Of course, this is a balancing act. Mark, remember this? So it's a trade-off. We're trying to develop features in our systems that enable us to scale them very rapidly and give our users all of the capabilities that they know and love and be highly available. But we want to balance it by not letting our costs get out of control. So this is not easy. If you think about it, it's an architectural problem. We've got to worry about performance. We've got to worry about scale. We've got to make our systems highly available so that users can always guarantee that they're there. And of course, they've got to be secure. These are all software architecture quality attributes, the things that we know and love and have been hearing about all day. It's just at hyperscale, they sort of acquire additional complexity because these systems don't behave in sort of expected ways all of the time. So we're continually making trade-offs when we deploy our systems in a cloud, and here's some on the slides here. Do we use reserved instances versus on-demand? There's a cost implication there. What about machine capacity when we allocate a VM? What instance type do we allocate? Are we over allocating resources, or are we going to under allocate to save costs and maybe slow down the performance? What about serverless function? When we configure a Lambda service, we say how much memory we want it to have, and then AWS calculates the CPU based on the memory. How do we know exactly what memory our system should be using? What about database storage tier costs? So Dynamodb is a lot more expensive than S3, which is a lot more expensive than Glacier. Can we tier our data across these so we can optimize costs, so that data that we don't access very often is living in a slow but cheap media, such as AWS Glacier? And what about database reads and writes? If you use DynamoDB or Google Data Store, you actually pay by the read or write. So if you can optimize your code so it's doing less reads and writes, so maybe doing lots of cache reads instead, then you're going to save money. And finally, what about database consistency? In DynamoDB, you pay more money to do a strongly consistent write. So do you need to do that? Because it costs you a lot more money if you do. Maybe you don't. Maybe you can engineer your system so you can live with eventual consistency. So if you're building in the approach taken by this excellent book on evolutionary architectures, these are the sorts of issues you can examine and experiment with using incremental changes. You can configure parts of your system to be deployed slightly differently with different configuration parameters. You can then set up traffic splitting, and then you can actually see how the system behaves without having a great effect on your users. And then you can make decisions based on the data that you've captured. So you're essentially making a hypothesis. If I change this parameter, will it be beneficial to my system? You set up an experiment, and then at the end of the experiment, you assess the data to see if it had a positive or negative effect. So you can do this using evolutionary architectures and sort of incremental approaches. But you don't always have an architecture that you're going to change. Sometimes you're just going to lift and shift a system into a cloud, or you're going to build a new service where there's no existing infrastructure. So you've got to make decisions based on just building a new service. And how do you decide how much that's going to cost? Well, you go to your cloud calculator, your friendly cloud calculator, and you make guesses, basically. And you hope that your guesses that you have to allocate resources match reality when you deploy, and hopefully match reality into the future. But optimizing costs using one of these things is kind of a hard problem. So about a year ago, we decided to start working with initially Google Cloud Platform, because they gave us some support in terms of credits, to see if we could do better than a Google a price calculator. So we started a project to do basically cloud performance analysis and scalability analysis. And the intent is that we have lots of variety, lots of heterogeneity, lots of choices that we can configure our servers to behave using different platforms, and our databases to live in different database technologies. And what are the implications of making these choices? So we have Google Cloud Platform, AWS. If we use App Engine, we have at least four different programming languages we can use. We can write to Google Cloud Platform SQL databases, or we can write to Data Store. On AWS, we have Lambda, or we can have our VMs, and we have a variety of databases as well. So what we're trying to do is come up with essentially a set of reference data that we can publish on a website so you can all see it, about how these systems behave under different scenarios, different loads, different read loads and write loads. And we wrote a Java client that we use at the moment, but we can easily configure to send requests to basically a use case which we run on the server. And what I'm going to talk about today is the work that we've done over the last few months, just using Google Cloud Platform, a variety of languages, and basically a parameter study on how App Engine behaves. This is what one of our tests looks like. So this is taken from a test, and So we have a Java client, it starts up and it starts firing in this test. It's actually a very write-oriented load. It's mostly doing writes. There's some background reads. And you can see we use a classic sort of load profile. So we start with a light load. This enables the system to sort of fill its caches and load the initial set of instances. Then we ramp the load up from this scale-up phase. It ramps up very quickly to a peak phase, which is the majority of the test. So the majority of the test, we're bombarding the system with requests. This is 1,024 clients all sending continuous requests. And then at the end of the peak phase, we scale down. So we give the infrastructure chance to release resources. So this is Google App Engine, so it's got the potential to release instances that it's already scheduled. So it's kind of a classic load testing profile that we have. So let's start with a real simple example. On my server, I can choose to write my server code. I've got the same database model. I've got the same database operations, but I write my server in different languages. Same API, same database operations, just the language in the middle that accepts the RESTful request, the HTTP request, validates it, does some pretty simple business logic, issues the database requests, and then returns, in this case, just a 201. So, does it make a difference? Who knows? That's why you do experiments. So, we did this. We fire exactly the same load at every single one. And you can see here, this is the sort of charts that we plot. And just taking the Python example down the bottom here, because I can reach it, you can see we get nice scaling. We start off 128 clients. This is the peak load. So peak should always be higher than the overall load, because the overall load includes the throughput for the phases where we weren't actually sending many requests. So it's always going to be, overall throughput is always going to be less than peak throughput, or it should be anyway. And then you can see it scales up nicely as we double the number of clients from 128 to 256. It's scaling up, and roughly 2,000, say 1,800 there to about 9,000 requests there. It's scaled quite nicely. That's Python. If you look at the other languages, Node, Java, and Go, they all scale with a very similar profile. But the values are different. So let's analyze what the values look like when we compare them. So this is for the peak low, the 1,024 clients, all 4 languages. And we can see quite a significant performance difference. So the Go server is actually really fast. Right? It's Google infrastructure, so maybe there's some internal bias there. But Node and Java are pretty similar, and Python performs well, but it's a little bit slower than the others. So just having the language, and these servers are not doing a lot of work, believe me. It's mostly the language infrastructure and allocating the instance to the serverless infrastructure, the time it takes to load the instance, which is making this difference. So this is interesting. Go's faster than Node, which is faster than Java, it's faster than Python. But what about costs? Costs are always an issue with clouds. So what we do is, from the Google Cloud Console, you can measure the amount of instance hours it takes to do a particular test. So this is the instance hours for these particular tests. And we average these over multiple tests, obviously. And so Go is actually not only faster, it's a lot cheaper. So I think it's about 17 instance hours to do this particular load, whereas Python's over 50. So it's about 3 times more in terms of the amount of resources that are being allocated. Java uses less, but Java instances take an awful lot longer to load than any of the others. The mean times to load a Go instance is like half a second, whereas the mean time to load a new Java instance, as we scale up, is about 7 to 10 seconds. So it's a lot more heavyweight to scale up, but once it's actually allocated, it performs pretty well. So of course, we know the performance, we know how much it costs, so we can calculate a price-performance ratio. And here we can see that basically, if you analyze it relatively, the Go code is giving you about 4 times the cost, the price-performance ratio, than Python. So if you want to just spend the same as Python, you can do it with 1/4 of the Go resources and still get the same results. So this is a reasonably significant outcome. And it just shows that a simple decision, such as choosing the server language that you use, is architecturally significant on a cloud in terms of cost. So, and potentially quite significant. So that was kind of the first result that we have. So choose wisely. The next one's even more interesting from my perspective. So when you deploy something to App Engine, we use a standard environment and it has something called auto-scaling. And there's 7 or 8 parameters that have default values that you can set when you deploy an instance. Just do it in the app.yaml file. So we thought, what happens if we vary these? What will the effects be on performance and cost? So these are the main 5. There's a minimum and maximum instances as well, which we just left as default. We didn't use them. So you can tell Google App Engine what target CPU utilization to aim for, and the default is 60%. So when an instance hits 60% load, Google App Engine will say, I think I should probably schedule a new resource because this one's busy enough. Then there's this slightly weird calculation that you can do on the number of concurrent requests that an instance will get allocated. And by default, what happens is you multiply maximum concurrent requests, which is 10, by target throughput utilization, which is 0.6. So in this case, by default, when an instance gets 6 or more requests running in parallel, Google App Engine will say, I need to allocate a new one because I'm scaling up. And then there's the latencies, minimum and maximum pending latencies. And these basically configure how long Google App Engine will wait until it says we've got a backlog of requests and I need to allocate more instances to start processing them. And it will never allocate a new instance less than minimum pending latency. It will possibly allocate some between the value of minimum and maximum, and it will always allocate a new one after maximum. So we just went with the defaults on this, as they're both the same as 30. And what we did was this is obviously a sort of an exponential problem. If we vary all these with different values, you end up running an awful lot of tests, and we just didn't have time to do all that. So we picked the CPU ones, the ones that are relative to controlling the CPU. And we designed a set of tests where we varied the CPU utilization from 60% to 80%, and we varied the maximum concurrent requests from the default of 10 to 90. We left maximum throughput as 0.6, so each of those values on the top, 10, 35, 65, and 90, would be divided by 0.6 before you actually schedule a new instance. And what we did was a parameter study. We just ran these tests multiple times and see how the performance of the system varies with these different settings. And it's kind of interesting. What you can do with these types of studies is just plot response surfaces. So this is showing a representation of the mean throughput, the throughput for the whole test. You can see we have the different max concurrent settings along this side and the CPU ones along that side, and the throughput is on the y-axis. So you can see with this response surface, the colors tell you the areas of the surface where the values are relevant. And it varies a reasonable amount. It's not so obvious on mean throughput though, because it gets smoothed out by the scale up and the scale down phase. It's much more obvious what's happening on peak throughput. You can see here the y-axis is only 7 to 8,000, but you can see that the max 90 is actually giving you less throughput. And around CPU 80 is probably about the minimum value that you're getting. And somewhere in the middle there, around somewhere between max 35 and max 65 and CPU 70, you're getting maximum throughput. And from a research perspective, what's interesting is whether this plot is predictive. Can we pick a point that we've actually not tested and see if it would actually be predicted by the surface? That's something we're still working on. So again, we can measure the instance hours, the amount of compute resources that were used in these tests. And so again, this plots those values, and you can see that the values on the left here, where the max concurrent request is 10, we're using a lot more instance hours. So this is the default setting, remember, and so it's allocating more compute resource because it's allowing less concurrent requests within an instance. Whereas as we increase that value and allow more concurrent requests into an instance, instance hours to do the computation is reduced, so it's cheaper. That means that as we say we can have more concurrent requests, and as we increase the capacity of the CPU, we spend less money. But how does that affect performance? So we calculate again the price-performance ratio, and this is a plot of it. And you can see the price-performance ratio is significantly lower with the default values. A max of 10 and CPU of 60. This corner here, there's no light on this. Is there a light? Yeah, it doesn't matter. Oh, what have I done? There you go. This corner is quite a low price-performance ratio, whereas we go to the other side where we're allowing servers to do more work before we scale up. We're actually getting a much higher price-performance ratio. But what does this mean in real terms, in real numbers? So these are the actual raw numbers for the peak phase, average throughput, and the maximum number of instances that test used. And so let's pick out a couple of points for you to sort of take away. This is the default setting. So if you deploy something to Google App Engine, those are the settings you get. CPU 6.6, max concurrent request 10. And so you see, actually in our test provides pretty high throughput. One of the highest, not quite, but there's a higher one there. It's 98% of the default provides roughly 98%, 99% of the throughput. But look at the difference in costs. Here we have 11 instance hours, here we have 9. So we're achieving, by varying our settings through this experimental procedure, if we set CPU to 70 and max concurrent request 35, we're actually reducing our cost by 20% and getting higher throughput. Win all round. That's great. So that seems like a really significant thing to know. And of course it will vary depending on your load and what you're doing in the actual servers, but it just shows that the default settings are, I would say, unlikely to provide you the best cost-performance ratio. So let's do another one. So in this case, we look at the default configuration, cost us 11 instance hours. And this one over here only cost us 6 instance hours, so roughly 54% of the default settings. What about the performance? Well, we're a bit slower on the values there where we have max concurrent requests at 90 and CPU at 70. But we're 96%-ish of the same performance that we're getting with the default settings. But we're significantly cheaper. So if your system is quite happy just dropping 4% performance, you can almost halve your costs by just paying attention to these parameter settings. Now, if you were spending millions of dollars, this might be a real big bunch of money. So, pay attention to details. because they can make a big difference. I love watching that. So again, I said this earlier, but it's something to remember. As you scale up your systems and you spend more money on a cloud, small optimizations can make real big differences in the bill that you get at the end of the month. And this requires you to potentially dig down into these parameters. And the interaction between the parameters for App Engine, it's just not obvious what happens when you change things. The only way you can find out is to run tests. And in this example, if you got really crazy, you could hypothesize that if you had an evolutionary approach, you could just configure multiple services with different parameter settings, deploy them all, set up traffic splitting to send requests to each particular one, watch it for a week, and then see which one's providing you with the best throughput and cost ratios. So it's not impossible to do this in a live system. So we're still working on this. We've actually got a lot more results, which I haven't had time to process because semester started. So this sort of stuff will start creeping onto our website. We'll push out in the new year, which you can all start to look at. And we'll summarize it. We'll also push out the raw results for the crazy performance research prediction community that exists in academia. They'll love it. They've never seen such. When they get a 700 megabyte Excel file, they'll be in absolute heaven. And we're also going to change our test cases. This is a very write-oriented test, and it would obviously be sensible to test more balanced or read-only type tests and have different configurations. And what's interesting is we use Swagger. Who uses Swagger here to define their APIs? So Swagger's pretty cool. It's horrible YAML, as Len was saying earlier, but once you get used to it. But we could potentially write something that would interpret a YAML description and then generate the code to call a particular service from our load testing client. And so it's not an infeasible task to do this, and I think that's one of the things I'm going to throw my students at in the new year, so that we can just say, here's an API, here's the load I want to exert on that API, here's some random values to pass in, generate me a client, run the thing, and off you go. You get results straight away. So that, I think, would be a really useful piece of technology. So, just in summary, these systems are hard because they have all these knobs and dials that you can tweak. And these knobs and dials are significant in terms of the way the systems behave. And because our systems are deployed in shared virtualized environments, and these environments are totally dynamic, you're never quite sure exactly what effects these tweaks on the knobs and dials of the configuration parameters are going to have. So the only way to find out is to experiment. And doing these experiments doesn't have to be super costly. And hopefully we'll publish some data that'll help you with some decisions, but there's so many cloud services and there's so many workloads, it's impossible to cover them all. But with careful design, you might be able to save a lot of money on your cloud bill at the end of the month. So that's about it. Just like to acknowledge the Google research for the credits that they gave us. We'll hopefully start with AWS, similar testing in the new year, and the students who worked on the project with me. That's it. Thank you. I can see hands.
Hello. So first of all, thanks for the presentation. The whole topic of optimization excites me a lot, and I would like to ask how costly and how difficult was it to run the test itself? Because you are talking about many knobs, and whenever there are multiple knobs, there's always the idea to automate that kind of testing, namely using machine learning to make the algorithm, because you presented the results of your work, which was only several knobs you chose. You chose some values, you run the tests, and I think that if you did it in the way you did it, then it must mean running the test is very costly. Is that correct?
We spent over $10,000 running this and another set of tests.
Okay, so do you
Not
think
too expensive.
it would be possible to maybe run some sort of simulation to implement machine learning on this topic, or is it the cost base for machine learning topic to run 1 million tests would be too great and inachievable?
I think you could potentially run multiple instances. If you could automate this whole process, we just haven't had time to do it, where you automate test submission, data extraction, data processing. You've got to also validate the data because you get quirky runs, it's the cloud, and you've got to throw out the screwy data that you get. And then you could feed it into a machine learning algorithm for sure. Whether it would produce interesting results, I don't know. I've not done it. But I know that once we publish this data for the software performance community, they will start doing this. So we'll soon find out.
Thank you.
Hello, my question is, the code you tested in different technologies is going to, is doing some I/O thing, like database, because if not, you cannot be sure that the one technology or the other is better, yeah?
Yeah, it's basically each of the servers is issuing reads and writes to Google Data Store. But the reads and writes are identical, so the cost of those per test is identical. So we can basically take it out of the equation.
This aspect was that serialization, or in the case of Java, reflection and so on, could affect performance. You know, that was my hypothesis.
Yeah, I mean, there's language mechanisms are what are causing the differences in language behavior for sure. But what we've tried to do is factor out all of the variabilities beyond that. So they're all doing exactly the same I/O when a request comes in. They're issuing the same API call, the same values. Okay, it's going through a different client library, but we can't do anything about that. So,
thank you.
Hi, Ian. One quick question. What are your thoughts on extrapolation when you're talking about measuring at scale?
I don't think it's a good idea because you really don't, these systems don't behave in a linear fashion. And so the measurements that we took with 1,024 concurrent clients may look completely different if we double the load. And there's only one way to find out, and that's to run the experiment. So I've seen many instances in my past where, you know, we've doubled load, or we've performed things in slightly different ways and got completely different load profiles. Len?
Yeah, I think you said this, but I don't see any reason why if you had a production system, you couldn't do these tests by setting the parameters for 1 week and then a different set of parameters for another, and doing it in production, so that the incremental cost then is maybe, you know, choosing a bad set of parameters or something, but the incremental cost for the test seems like it could be almost negligible.
Yeah, that's right. And if you do choose a bad set of parameters, hopefully it would be pretty obvious immediately, and you could kill that instance off and just concentrate on the ones which are still giving you good performance and good cost.
And then you would have a realistic measure, a mixture of reads and writes, you know, because it's what your workload generates.
Yeah, exactly. Yeah, I think you can do this sort of parameter study in an evolutionary architecture environment. So there.
Yeah, so thanks for the talk. And just a silly question maybe. I think this is a continuous process, no? Because if the architecture changes, then you need to repeat the tests and analyze again the data.
Yeah, continuous exactly, because also you don't own the infrastructure. So if Google changed the code on App Engine, or while we've done this test, they've actually renamed Data Store as Firestore, is it, George? I can't remember the new name. And the API we're using is slowly being deprecated. So yeah, it's a continuous process because the environment underneath you don't control, and it's subject to code changes all the time. So yeah. Got another one at the back.
Good afternoon. My question is, from your experience, do you think it's reasonably easy to automate these kind of tests and to have continuous feedback on this, a bit taking the comment of Lynn?
It's not easy. Processing the results is non-trivial because, like I said, these things are generating millions and millions of logged requests that we have to process in terms of latencies. So you need some infrastructure to enable you to do that. I think automating the client side is not that difficult if we can presuppose some sort of Swagger-based API description. But actually the data processing is non-trivial. Things like calculating the 99th percentile, we do that, we have that value for all of these tests. But when you're calculating the 99th percentile of 20 million requests, it's not a trivial calculation. Excel won't do that for you. So you have to use some sort of window-based algorithm or some bucketing type algorithm to do that. So yeah, it's not easy, but I think if we put our mind to it, then we could probably get tools out there that would enable people to do it.
Thank you.
We're done.